So hi everyone, we would like to welcome you all to this talk of the IEEE GRSS-APS-SSCS student chapter at the University of Southern California. Today we are pleased and honored to have this talk presented by Professor Natalia Nikolova entitled Microwave and Millimeter Wave Imaging for Biomedical Applications. Professor Natalia Nikolova is a professor at the Department of Electrical and Computer Engineering at McMaster University, where she leads the Electromagnetic Vision Research Laboratory. Her interests include inverse scattering, microwave and millimeter wave imaging, as well as computer-aided analysis and design of high-frequency structures and antennas. Professor Nikolova has authored more than 300 refereed manuscripts, 7 book chapters, and 2 books on the subject of microwave imaging. She has delivered 54 invited lectures around the world on the subjects of microwave imaging and computer-aided electromagnetic analysis and design. Professor Nikolova, we would like to welcome you again, and the floor is yours.
Thank you very much, Michelle, and thank you for inviting me. Probably the best interactions that I have had during my lectures were exactly when I was presenting to joint student chapters. And so let us get going with the lecture because we have a fairly limited time. And so, of course, today I will be talking about microwave and millimeter wave imaging, in particular for biomedical applications. So you should be aware that microwave imaging of tissue goes quite a way back. The first systematic studies date back to the early 1970s, mostly by the team of Larson and Jacobi in the United States, and with the first articles starting to appear in the late 70s, and even a book, for the very first book on medical applications of microwave imaging in 86. They were experimenting mostly with canine kidneys, as is shown here, attached here to a wooden dowel in this particular experiment, and scanned laterally, that is in the 2 lateral directions between the 2 antennas, one transmitting, one receiving, everything submerged in water, because it was by that time already clear that the electromagnetic, or if you wish, permittivity properties of the canine kidney were much closer to water than in air. And so if you want to couple power, you better make sure that the surrounding medium is well matched to the object that is being imaged and that your antennas are designed to operate in water. And here you see the dissection of the organ, visibly appreciating the differences in the various tissues that the kidney is composed of. And to the delight of the researchers at the time, when they plotted simply the magnitude of the measured transmission coefficients S21 as a function of the scanned position, they could indeed see quite a bit of detail which correlated very well with the distribution of the tissues inside the organ. More importantly, as expected actually, the copole S21 plots and the cross-pole S parameter plots showed fairly complementary or different information. And as expected from the copole plots, they capture better the edges and smaller inclusions inside the object, whereas the copole measurement provides a better overall mapping of the permittivity distribution of the object. So with this example, we now come to appreciate what active microwave imaging is about. You should be aware that there is also passive microwave imaging. I'm not going to talk about it here. In active microwave imaging, we intentionally generate microwaves, and the hope is that this radiation will penetrate and interact with the interior of the imaged object, thereby generating scattering. As long as the scattered waves make it out of the imaged object, and if we can collect them Typically, we collect them with antennas over very large apertures that are electrically on the order of several, even tens and hundreds of wavelengths. Then we can process the so collected scattered data and generate, using image reconstruction algorithms, the object's electromagnetic property distribution. Just like with Larson and Jacobi, typically the measurement of an object is a two-stage procedure. First, we perform a measurement in the absence of the object. You can view this as a calibration measurement. Typically, it is referred to as baseline measurement. And that is because in such a measurement, in the absence of the object under test, there are responses. These responses, say as parameters, are referred to as incident field responses. Then the object is inserted and it is measured, and the responses that are being acquired are referred to as total field responses. And total field because they can be viewed as a superposition of the incident field responses together with scattered field responses that are due entirely to the object. By now, you probably appreciate that the information about the object is carried by the scattered field responses or data, not by the incident field. And so actually, normally, we strive to de-embed the incident field or baseline measurements from the total field measurements. There are several approaches to do that, but the simplest one is simply to subtract the baseline data from the total field data in order to obtain the scattered field data on which our image reconstruction methods operate. The early imaging experiments and research that was carried out more than 30 years ago provided great insight that to this day we use in our research. First of all, it was concluded that with measurements in the gigahertz range in tissue, we can achieve a resolution on the order of a centimeter, even several millimeters. However, through studies of the electromagnetic properties of tissue and the attenuation, the researchers quickly understood that a compromise will need to be made between resolution, spatial resolution, which is better at high frequencies, of course, because the wavelengths are shorter, and the penetration depth, which unfortunately is better at low frequencies. And so a lot of research was done on the optimal frequency range for imaging that require depths on the order of 10 to 15 centimeters. For such penetration depths or image depths, it was recommended to use definitely the low gigahertz range, and which exactly range to choose depends on the reconstruction method. And so, bearing in mind the resolution on the order of centimeter, the penetration depth on the order of 10 centimeters or so, the most promising applications with low gigahertz measurements were viewed and continue to be viewed as breast cancer screening, brain stroke diagnostics, and bone disease monitoring. On the other hand, in the millimeter wave range, where the penetration is only a couple of millimeters, the most promising applications are skin cancer diagnostics and skin and dental health monitoring. Why do we care about microwave imaging as applied in biomedical diagnostics? That is because the modality has certain advantages, such as being safe because it is non-ionizing. At the power levels that we employ, the specific absorption rates are very low and they pose absolutely no harm. Therefore, frequent checkups on patients are completely possible. The equipment, especially in the low gigahertz range, is low cost, compact, low maintenance. And so the aim is, particularly with breast cancer screening, is to deploy the equipment in family doctors' offices, which is totally impossible with CT machines, mammography machines, or MRI machines. And so the technology is considered very promising and well suited for mass screening and monitoring applications where patients are to be seen on a frequent basis. The disadvantages, of course, compared to MRI and CT X-ray computed tomography, is the limited penetration. Deep body imaging is not feasible, such as cancers in kidneys or liver. That's impossible, at least now. And the relatively low resolution, which is, as we mentioned, only sub-centimeter resolution. If you compare this with the sub-millimeter resolution of CT scans or the millimeter wave resolution of MRI, obviously we cannot compete with those. However, for the purposes of screening and monitoring, such high resolution is not necessary. Breast cancer screening in particular is in great need for alternative modalities. And when I'm saying alternative modalities, I mean alternative to mammography, which is the usually employed modality for breast cancer screening. Obviously, early stage detection is critical. It is well known that if the malignant mass is removed before it reaches a size of 15 millimeter, survival rates are very, very high. On the other hand, the detection of such small-sized tumors is the problem. And the problem with mammography is that it has very high false negative rates. That is, it misses small tumors very often, particularly in radiologically dense breasts, which are more typical for younger people. Not to mention that it is ionizing and it requires quite severe compression of the organ. The dense breasts is the real concern, because then the sensitivity, that is the ability of identifying a tumor, drops dramatically from the average of 85% to 50%. 50% means that 50% of the tumors are essentially missed. And this is really not sitting well with radiologists. In fact, in the case of dense breasts, they always recommend ultrasound as a complementary modality. Ultrasound requires highly trained operators. It is never a good screening modality on its own, but when paired with mammography, it is very useful. MRI is a great, magnetic resonance imaging is a great screening modality, it's a great imaging modality for breast. However, it is not suitable for screening because it is so expensive. A single screening for a single imaging session for breast cancer can cost anywhere between $1,000 and $3,000 depending on where you are. It requires the injection of gadolinium, which is a contrast agent. It requires anywhere between 30 and 40 minutes, and so it is definitely not suitable for mass screening. Coming back to microwave imaging of the breast, there are quite a few challenges, and maybe that is why it hasn't entered clinical practice yet, despite the fact that there are quite a few prototypes reported in the literature. The propagation environment is fairly complex, involving multiple diffraction, reflection, and refraction, so the signal paths are very complex. This is due to the fact that the anatomical detail of the tissue composition inside the breast is on par or comparable with the wavelengths which in tissue in the low gigahertz frequency range are between 9 millimeters and 30 millimeters. And this is the size of the little tissue inclusions that we see, say, in high resolution MR images. This propagation is far more complicated than the case of X-rays, where the computed tomography propagation model is a straight line. And so here I wanted to give you an idea of the complexity of what we are imaging by showing a transfer slice of a T1 weighted MR breast image. And you see here in dark the fibroglandular tissue or stroma, the adipose or fatty tissue in white. You can see the skin outline. There is also, of course, muscle, and behind the muscle, there is bone from the chest wall. And so in order to perform imaging and to conclude whether we can actually image tumors, we need to know what the constitutive parameters are of healthy tissue versus malignant tissue. For that, we perform dielectric probe measurements, as this sketch is showing here, on a tissue sample using dielectric probes and a vector network analyzer in order to measure the complex permittivity, real and imaginary part. Here you see the probe inserted in a tumor, or at least visually, this is considered to be a region of tumor. And we also measure in the adipose or fatty tissue, fibroglandular tissue nearby, etc., etc. And we want to see whether there is contrast. Well, there is one problem here. And the problem is that when we measure what we perceive to be a tumor, when we look at the microscopic image of this area, we are being told that by radiologists that tissue is never just cancer. I mean, cancer on a microscopic level is interdispersed with healthy stroma or fibroglandular tissue, the reddish one. And so what we measure is really a mixture of cancers and healthy tissue. And so it is always expected to have some wide variability in the constitutive parameters of what we measure for the particular tissue, in this case, breast tissues. On the left plot, you see measurements reported by the team in Japan, Professor Kikawa's team, and you can see here the cancer, the stroma, fibroglandular, healthy tissue, adipose, fatty tissue. On average, there is contrast, and the contrast can be anywhere between 50 to 100%, depending on the frequency range. However, because of the wide variability, there is also a lot of overlap between the cancer's permittivity values and those of healthy fibroglandular tissue. The same thing repeats with the effective conductivity of the tissue. And so we say that there is a relatively weak but sufficient contrast to perform microwave imaging of the breast. Finally, our biggest challenge is that there is strong dissipation in the tissue. And as an example for breast cancer imaging, I'm considering a simple plane wave model, which can give us an estimate of how much power dissipation we can expect for a given thickness of breast tissue, for example, 5 centimeter thickness of radiologically very dense breast, which is essentially just fibroglandular tissue. And we can see that just within 5 centimeters of tissue thickness, we see an attenuation on the order of minus 60 dB. So that's a lot of attenuation, which is telling us we will be dealing with very weak scattered signals. We need high dynamic range of the measurement system with high quality, low clutter measurements. And so designing the imaging system is really the real challenge in microwave imaging in biomedical applications. Of course, we have to follow certain common rules. We have to reduce motion artifacts, and we have to aim at collecting as much data as possible. The reduction of motion artifacts is achieved typically by prone patient positioning, as is shown in MRI imaging of the breast. The patient, while breathing, when in prone positioning, will not move the front chest wall, and therefore the organ is not going to move. In mammography, which is illustrated in the photo below, on top of it, we have compression, and therefore there is absolutely no motion artifact. But the compression in mammography is so severe, as you can appreciate from this photo, exactly because X-rays are struggling with dense, radiologically dense breasts, and to improve the contrast in the image, they have to flatten the organ or reduce its thickness. To collect as much data as possible, you're probably all microwave and antenna engineers already. So, of course, we need multiple observation locations, if possible, multiple illumination locations, if possible, employ two orthogonal polarizations, just like in the experiments of Larson and Jacobi, and multiple frequency samples in a wide band to have a compromise between good penetration at low frequencies and high resolution at high frequencies. Of course, prior information and imaging is always helpful. So different prototypes have been reported in the literature, cylindrical scans, typically in a multistatic arrangement, as is the one shown here on the left, where at every given measurement, one antenna transmits, all others receive, and in the next measurement, another antenna transmits and all others receive. And this has been realized with the first ever prototype for microwave imaging of the breast by the team of Professor Meany at Dartmouth College, which is shown here. Typically, the scanning along the circle, as shown here, is done electronically, employing RF switching with these antennas. The vertical scan, unfortunately, is mechanical, and this makes the data acquisition a little slow. Hemispherical scans have also been proposed and prototypes have been developed, such as the one on the left, where we see a hemispherical shell for accommodating the breast organ with 60 slot antennas. And each one of these antennas can transmit, and each one of these antennas can receive. And this gives you quite a few data points. You can see that these antennas are actually connectorized with SMA connectors, which lead to a 60-port RF switch and then to a VNA. The system developed in Japan by Professor Kikawa's team is also hemispherical, but a little simpler because we have only 8 slot antennas that transmit in a line of array and an orthogonal array with antennas that only receive. But in order to have sufficient viewing angles, this array is mechanically rotated around its axis. At McMaster University, following the advice of our radiologist and biomedical imaging experts, we are developing a planar scanning system such as in mammography, where the organ is to be placed between two flat plates and scanning is to be performed on planar surfaces. Here you see a photo of an experiment just about to start with the breast imaging phantom enclosed here in this box, and very simple mechanical scan with one antenna on top and one antenna at the bottom. And you see here the translation XY stage or scanner, which moves the object between the antennas along X and Y. Now we are moving, of course, toward electronic scanning because mechanical scanners are just terribly slow. No patient can wait for half an hour or 1 hour to be scanned. And so electronic scanning is challenging. And on the other hand, planar scans are very amenable to electronically switched arrays realized on PCB technology. So these are arrays where we do not want to scan. They're just pressed against the tissue, so no mechanical scanning. And the array, the receiving array, each antenna is switched one at a time to receive the signal. And this is our prototype 2, where we wanted to compare a passive antenna element, such as the one here, versus an antenna element which is equipped with a low noise amplifier, an LNA chip. Sure enough, we found out that the signal to noise ratio is much improved if you have an LNA chip. And so here you see the measurement on a breast phantom made of carbon rubber slabs, custom made. And so now we have moved on to our prototype 3, where we will have, or we actually already have, an active antenna array where each antenna is equipped with a low noise amplifier chip. The overall antenna array is 16 by 16 antennas, or 256 antennas. And these antennas, this array is actually built with 4 identical PCB tiles. One such tile is shown here, and it accommodates 4 rows of 16 antennas, receiving antennas. The LNAs lead to vertical high-speed connectors from high-speed computing technology, which vertical connectors are used to connect the receiving active elements to their respective mixer circuit boards, which are plugged inside these connectors. On the right, you see that now these prototype 3 boards have also heat sinks on top of the LNAs to prevent any excessive heating of the boards. And you can see test boards with SMA connectors inserted in these vertical high-speed connectors in order to test each element of the array. Some promising clinical trials have been reported in the last 10 years or so, especially in the case of larger carcinomas. Here you see some results which are presented by the team of Professor Craddock in the University of Bristol in the UK. And you can see the microwave image of a fairly large carcinoma. This is a large tumor, 17 millimeter in size. And the mammogram on the right. So the microwave imaging definitely works with relatively large cancers. It is, however, a little bit more difficult to deal with the small cancers. Very similar result with a relatively large tumor mass has been reported by the team in Japan with their hemispherical scanner, where a relatively large tumor is being identified by the microwave images as is shown here. At McMaster, as I said, we are still working on tissue phantoms. We are not ready to go to patient measurements because our systems are still slow. And but with tissue phantoms, here you see one such example, which is a 55 millimeter thick flattened breast phantom, where in layer 2 and layer 4, there are inclusions of tumors. And for total, you see the brown mixture, which represents scattered fibroglandular tissue. You see the whitish area, which is a phantom for fibroglandular stroma tissue. We ran the phantom through a CT scanner in our health sciences CT scanner. And obviously, the CT scanner identifies the inclusions very well. I mean, it has 0.5 millimeter spatial resolution. The microwave images are 2D projection images because we use only transmission measurements. We don't have depth resolution. So the images that we have are mammography style, 2-dimensional projection images. It is clear that we can find the inclusions, but it is also clear that we do not have sufficient spatial resolution to tell that these are actually 2 objects right next to each other, not one. And so, but this is expected because the center-to-center distance for those guys is 8 millimeters. So no surprise there. So how does microwave imaging work? Very quickly, of course, we need measured data. This slide really is showing you how interdisciplinary imaging is. We need measuring data, and therefore we can perform either ultra-wideband frequency sweeps using VNAs or ultra-wideband pulsed radars. We need antennas. So this is microwave and antenna engineering in action. So this is the hardware side of things. But on the soft side of things, first of all, we need forward models. We need mathematics that predicts what is the relationship between the measured data D and the unknown contrast of the object that we are measuring here, denoted with X. Now, we know that the permittivity of the medium determines also what is the field distribution in the medium, as follows from Maxwell's equations. So, of course, the data equation, in order to relate the permittivity to the data, has to go through the field. And on the other hand, the field has to satisfy Maxwell's equations. For all of these models, essentially, we're using the models provided by mathematical physics in electromagnetism. And then finally, once we have these models, we have to invert them, because what we know is the data. What we want to find is the dielectric properties. In this inversion strategy, whatever it yields for the dielectric property is going to impact our E field. So we have to keep in mind that in effect, we also have to ensure that Maxwell's equations are respected. And so all these inversion strategies are the subject of applied topics in applied mathematics, such as linear and nonlinear solvers, optimization methods, sensitivity analysis, etc., etc. Let us consider one of the simplest fast inversion methods in the frequency domain, termed quantitative microwave holography, and that is because it can recover images of the real and imaginary part of the permittivity. So let me show you what we have to deal with. Here is your typical data equation. On the left, you see our data, measured as parameters, actually the scattered portion of them. And now we have a model that predicts how the measured S parameters depend on the complex permittivity contrast, which is nothing but the difference between the permittivity of the object under test and the background permittivity. Now we see that there is a strong relationship to fields. The red term is the Green's vector function, which is actually also the incident field generated by the receiving antenna if this antenna were to transmit. Whereas the total field is the one that is generated by the transmitting antenna in the presence of the object under test. And on top of it, it depends on the permittivity contrast. So now that we know how the data is related to the field and to the contrast, we gotta talk about how we're gonna invert it. Well, for fast image reconstruction, it is highly recommended to first linearize your forward model, which means that you will be reducing it to a linear system of equations. And in order to linearize this forward model of scattering, let me go back and remind you that these fields are divided by known constants, so we refer to them as normalized fields. So these incident fields, so this is the incident field, our Green's function, but that one is supposed to be the total field. But we are going to make an approximation. We are going to replace it with the incident field of the transmitting antenna, which is known as the Born's approximation. And now I have a linear integral equation in the unknown contrast. These fields are assumed known. In fact, in imaging, we usually replace this dot product with what is referred to as the data point spread function, which is the system response to a point scatter. And this is what we assume known. So if the data is known and if the PSF is known, now the question is how we get a fast solution for the unknown contrast. A little bit more on the PSF. Now, the PSF, as I said, The physical meaning is that it is the measured response set acquired with a point scatter. So imagine you've got a very small point scatter in the middle of your imaged volume and you measure it. Well, what you measure is exactly the point spread function of your radar system. In mathematical sense, the data point spread function is nothing but the spatial impulse response of the radar system. You can easily understand all of these two bullet points by examining this equation and assuming that your scatter is just a delta function of space. Due to the sampling property of this delta function distribution, immediately you see that what you will measure is indeed proportional to the point spread function of your system. Here, delta epsilon RSP and omega SP are the contrast of the scattering probe that you're using to measure the PSF, and omega SP is the volume of the probe that you are using to measure the PSF. But that said, knowing the analytical form of our PSF helps a lot, because we can also assume analytical approximations for this incident field. We can also simulate these incident fields for our transmitting and receiving antennas. So all these forward models are extremely useful in order to derive the PSF of the system. Once we have the PSF, assuming uniform background, we immediately notice that our integral is nothing but a two-dimensional convolution between the PSF, the data PSF-H, the impulse response of the radar function of the radar system, and the unknown contrast. You probably by now, all of you know that convolution is computed in the fastest manner in Fourier space, because a convolution integral over x prime and y prime, the imaged positions, in Fourier space reduces to a simple multiplication of Fourier transforms. And so if I take the Fourier transform of my data, now my data is cast in k-space as a function of the Fourier variable kx, which corresponds to x, ky, which corresponds to y. Now this integral here in x and y becomes a simple multiplication. What remains is the integral over z, but that I can discretize into a sum. And now I have a very small system of equations, because this equation here can be written for all sorts of responses at all sorts of frequencies. So you actually have quite a few equations stacked on top of each other for each frequency, for each type of response. The columns are coming from the value of the unknown contrast, or rather its Fourier transform, as a function of range or depth. And so ultimately, we do reduce the three-dimensional integral equation into a very simple set of many, but small systems of equations which are solved in Fourier space. As is indicated here, a system of equations is solved independently, decoupled from the other systems at each point in Fourier space. If we have measured nx sample points along x-axis and ny sample points along y-axis, then the number of samples in Fourier space is also nx and ny as follows from the properties of Fourier transforms. And so we need to solve nx times ny systems of equations. And those are quite a few, typically 10,000 to 100,000. However, the systems of equations that we solve are small, with a typical number of size of the system matrix A on the order of 60 times 5. And so the computational complexity, it can be shown, is actually proportional to the number of sampling points, nx and ny. Whereas if you are solving the system of equations in real space, the computational complexity would be the number of sampling points cubed. And that is why real-time imaging pretty much always is done in Fourier space. Once we recover the contrast in Fourier space, then we can perform inverse Fourier transform and go back to the permittivity value, complex permittivity estimate in real space as a function of the imaged position x prime, y prime, z prime. This is the contrast. If you want the total permittivity, you have to add it to the background permittivity, which is assumed known. And this is actually the method with which these two-dimensional images have been obtained here for the this particular phantom. While the measurement with the mechanical scanner took 2.5 hours to sample densely with the 3 millimeter step, these images were reconstructed in less than a second. So at the moment, the bottleneck really is measurements, and that is why we are working so hard to develop an electronically scanned imager for breast cancer imaging. And let me take the remainder of the time that I have to talk a little bit about millimeter wave applications. My team works mostly on millimeter wave imaging in air, employing off-the-shelf radars, which are currently available on chip. We haven't done ourselves millimeter wave imaging for biomedical purposes. However, I do follow the developments in the literature with great interest. And I have noticed a lot of applications of the emerging millimeter wave technologies above 30 gigahertz in a number of sensing biomedical applications, such as non-invasive blood glucose monitoring, vital signs monitoring, dental health, wound healing, but this is all monitoring and sensing. On the side of imaging, there are a lot of papers, well, not a lot of, quite a few papers in millimeter wave imaging for breast cancer, which in my opinion is not going anywhere, which is to be expected because the penetration is very low and the sensitivity of our current imaging setups is low, mostly due to clutter. However, skin cancer, in my opinion, is very promising. Although diagnostics so far has been demonstrated only ex vivo on excised tissue or skin samples, but the results currently show that skin cancer imaging for melanoma, BCC, and other types of skin cancers is promising because the cancer is shallow, only 1 to 2 millimeter depth in the dermis, and there is high contrast actually in the dielectric properties of healthy skin and malignant skin samples. Here you see the estimate for the penetration depth at frequencies above 30 gigahertz. And you see the penetration depth is already dropping below 1 millimeter when the frequencies are above 30 gigahertz. And that is why I think that really the most feasible application is skin cancer. And there is an interesting work reported by the team of Professor Tavasolian at Stevens Institute of Technology on particularly BCC type of cancer, not necessarily melanoma. But here you see an excised skin sample, and the radiologist has outlined here on this stained histopathology sample where the malignant areas are. That's BCC, basal cell carcinoma. And you see the millimeter wave image at depth 0 microns. This means right on the surface of the skin, which is actually very interesting because this is supposed to be non-invasive. And indeed, this is an image which would hold the most diagnostic weight. Although the authors do report also images at larger depths, and they do confirm that indeed this is where the areas are red, this is where the malignant tissue is supposed to be. And so I think this is promising. And so to summarize, there is a lot of research effort currently on millimeter wave and microwave imaging, as well as sensing for biomedical applications. And a lot of effort is currently devoted on developing software tools, particularly, obviously, reconstruction algorithms, in particular, fast quantitative methods. Be it iterative or non-iterative, it is critical in biomedical imaging to produce the images fast. At the same time, we would like to have enhanced resolution and quantitative result. In other words, it would be good to know what is the permittivity and the effective conductivity, because this directly relates to the malignancies of tissues. Another very interesting, in my opinion, research effort is in devising calibration strategies that employ the measurements of known objects. Those can not only lead to better de-embedding strategies where the background signals are de-embedded more effectively, but they can lead to reducing clutter, radar clutter, which is very strong in medical imaging situations, and may even enhance the resolution. Very hot topic is compressed sensing, because biomedical measurements must be performed quickly. While we can reconstruct images quickly, we are still taking way too long to perform the measurements. But that is because we need a lot of data points. If we can reduce the number of data points and compensate for the lack of data using compressed sensing, then that would make the measurement system faster and simpler. So on the side of hardware, a lot of work remains to be done. Currently, we are not seeing clinical applications of microwave and millimeter wave systems, exactly because of the deficiencies of our hardware. We need novel architectures for faster measurements, possibly with switching at the level of intermediate frequencies. I don't have time to go into that, but this will allow to switch hundreds, even thousands of array elements within several seconds. More importantly, such arrays would allow for a MIMO, multiple input, multiple output capability, which translates into a lot of data points. Linear frequency modulated radars, while employed widely in millimeter wave imaging, including biomedical applications, are still not developed for low gigahertz range biomedical applications. However, linear frequency modulation radars are very promising in terms of providing the best spatial resolution in depth, in particular, for the given frequency bandwidth. And then finally, as I said, electronically switched architectures and arrays are critical, both in millimeter wave and microwave regimes. A lot of effort is also now dedicated to millimeter wave dielectric spectroscopy, that is measuring or monitoring the complex permittivity of tissues in the millimeter wave range. because in this range, it has been already established that in many, many types of tissues, disease leads to significant changes in the permittivity of the tissues. And I don't work in this area. However, I think that a lot of biomedical sensors that are very useful may come out of this millimeter wave dielectric spectroscopy trend in the current research. And finally, I would like to thank you and put here some more recent reviews on microwave and millimeter wave imaging applied in biomedicine. Of course, I'm also giving a reference to some of the review papers that I wrote some time ago. And so thank you very much for your attention.
Thank you very much, Professor Nikolova, for the nice presentation and the great motivating talk. Now we will open the floor for questions.
I have a couple of questions, but I will wait in the audience. I guess we have a shy audience today. Well, thanks again, Professor, for your talk. I really enjoyed it. I have a couple of quick questions. One was about, I think, slide 27 that you were you were explaining that this method is real time. Did I understand that this is not an iterative method, right? It's just
No,
okay.
no, this is a direct solution of a linearized data equation. That is why it works in less than a second on a MATLAB code, unoptimized on a laptop.
Sure.
So direct or linear reconstruction is very, very efficiently done in Fourier space. But we are doing work on nonlinear iterative methods as well, but there is no time to discuss this here.
Sure. I was just curious on the accuracy of the retrieval. I'm part of the work that I do is try to have a spectroscopy imaging system for soil, and a lot of the concepts, of course, are similar. I'm just using other material. One of the things that I'm kind of trying to say in the linear regime and not going to BIM or iterative solver.
Yeah.
I think one of question I was actually also reading one of your paper recently that is discussing about the validity or the validity range of Born approximation or Tikhonov. Would you mind to comment on the validity range and the contrast and sort of the size of the region of interest that you're looking here, and what would be that?
Right. There is a lot of misconception, in my opinion, and your question is very good about the validity of the linearized model of scattering. Number one, it is one thing to have the mathematical limit, which is telling you that in the case of, say, Born's approximation, the multiplication of your contrast times the volume of your target has to be less than 1%, and obviously you will be violating Born's approximation limits every time you're measuring. The thing is that when you violate Born's approximation or Ritov's approximation, depending on which one you're using, the errors that you are making do not necessarily translate into quantitative errors. They translate into image artifacts. And if you know that, and if you know where the artifacts may happen, you can actually image with much higher contrast. Let me give you an example. This method of microwave holography that is described here, in a slightly different form, of course, is applied in all airport whole body scanners, right? You are aware of millimeter wave scanners, are you?
Yes, the TSA.
Right, right. So these are millimeter wave scanners. They use a slightly different version of what we do here, and they produce qualitative images, just reflectivity, right? Well, what do you think is the contrast between a handgun and air?
It's a lot.
It is just infinity.
Right.
Nonetheless, if you look at their images, and I have them in some other presentations of mine, you can look at the papers of Sheen and McMacken, all these people who developed the first image reconstruction methods for whole body scanning at airports. You can see the weapon wonderfully. Are there artifacts where the total field is not estimated properly by the assumption that it is an incident field? Of course there are artifacts. But just by looking at the image, you know if there is a gun or a bottle of water or even a keychain. And so, as I said, we have to be very careful when we declare the Born approximation inapplicable, because practice already shows that actually with certain filtering, there are certain image reconstruction methods which are more prone to artifacts than others. Holography, in my opinion, is pretty stable when it comes to the artifacts are typically showing up with weaker intensity compared to actual images. But what I'm saying is that these methods are already working in working imaging systems, and they work with contrasts that are practically infinity. So that's my answer. Yeah, it's a little long, but it is also a complicated question.
So I guess my takeaway here is that we can still have some hope when using Born approximation on the quantitative level, but we might expect artifacts if we go beyond such a range.
Right. Have a look at these images. So these are microwave images, right? This is clearly an artifact. Where is it coming from? Where the phantom meets the background medium, which, by the way, is just microwave absorbing foam. And of course, because there is some scattering there, which has nothing to do with the incident field. In other words, the total field here is completely different from the incident field. And it just shows up in the image. I personally think that these dip in the value of the permittivity is also an artifact. But can you see these high contrast scatters, which are of permittivity 40, relative to here, the fibroglandular tissue is 30 or 25, if I remember correctly? Yes, you can certainly see them. There is definitely something there, right? And on top of it, because we have measured our point spread function, we didn't employ any analytical assumptions here. We measured our point spread function. We measured this by performing this measurement on our phantoms. You see that the permittivity values are pretty convincing, bearing in mind that that is a projection image, which means that these permittivity values have been averaged over the depth of the phantom.
Makes sense. ask a very quick follow-on question? I know you have another meeting at 2 p.m. with the series of motion meeting.
Right.
So what would be your thought on when we are using a linearized method, if we have some a priori knowledge in terms of the shape or the boundaries that there is large contrast, do you think that knowing that shape or geometry would give us some relaxation on the bone or the contrast that we can handle with the linearization method? Or how do you think about that? Or they're not too much related?
Now, holography itself leads to a model like this, which is a convolution, if and only if your background medium is uniform. What you're talking about is non-uniform background, right?
Um,
And that, in my opinion, can be resolved only by additional iterative, maybe non-iterative, but mostly iterative method where you will employ constraints for the values of the permittivity in real space.
Thank you so much. I learned a lot. I probably would just need to go back and watch the video. I appreciate your time. It's so an
No
honor
problem.
having
My
you today.
pleasure.
Yeah, thank you so much, Professor Nikolova, for your time. We know how busy you are. Thanks a lot. And thank you all for attending the talk, and stay tuned for upcoming events.